Okay, today we learn this thing called binary search tree. We already learned tree in that heap data structure. So binary search tree also use trees. It's just a different type of tree with specific properties. Let's briefly do a recap for what is a tree. We know a tree is just like something like a linked list, just one node connected with another two nodes. And especially for binary tree, usually one node can only connect at most two nodes. And the node on the very top, we call it root. And the left one is left children and right one right children. And so there are some terminologies we didn't talk before. One is called length of the path. So for example, from 60 to 57, there's a length, like 60 to 55 and 57. We call it, this is like a path, and the length of the path is 2. And the depth is similar this way, except this counted the, for example, from 60 to 57, the depth is 2. It's like you have 2 levels of to reach this node. And similarly, 45 is also here, the depth is 2. And because 45 and 57, they are in the same depth to the root node. So we say they are in the same level. And also all these nodes that has no children, we call it a leaf. And this is the root, this is like a leaf. They are at the very end of this tree. And also the head is like, for example, this tree, the head is like the maximum level. This tree is the head is 2. But if for example, if 67, there's another node here, although all these nodes, they don't have children, but the head of this tree will be increased to 3 because of that additional node. So head is like the maximum level in this tree. And a binary search tree is, so for every node, its left children is smaller than it, and the right children is larger than it. So we have this specific data structure at smaller, this one smaller, this one larger. So we can actually use many, for example, if we just traverse the tree in a specific order, this is like all these things will be an increasing order. It's like so if we just construct a binary search tree using this way, we can just sort it all these numbers just by creating this tree. And so to define the tree node class is just defined like this. We have an element and 2 pointer point to these 2 children's, and also you mean but for the heap? You mean a heap, right? Yeah. No, it's not that the same. You know, heap is using for heap is the node on the root is the largest one, right? All these children are smaller than it, but binary search tree, its right children is actually larger than it. That's the difference. Yeah, they are kind of similar, but this difference actually makes the. So if you, we will talk about later, like if you using a heap to order a number, a list of numbers, you can just get the first one, root one, reconstruct, get the root again like this way. But for a binary search tree, actually we don't need to do that. We can just traverse one time, like 45, like this way, and it's already sorted. More? My search.
Not search, like we use the binary search, like the mid value, find the mid value.
Yeah.
High, low.
Yeah.
Do this follow the concept?
Yeah, that's right. So the binary search tree is a very good way to do binary search because it's already like binaryized, right? And left side is smaller, right side is larger. We actually have a slide later to talk about that. Yeah. So yeah, you can see we can do a binary search on a binary search tree. Like we just compare the search this element. We just compare the current node with this element. If it's smaller, we check the left side. If it's larger than the current node, we check the right side, and else, which means the E is similar to the current node, we can just return true, we find it. Otherwise, we cannot, we didn't find it. So we can just using this way, search left, search right to find that element. So to insert a new node to this binary search tree is very easy. We just insert it to the leaf node. So we can just compare it to see if it's larger. We just go right side and larger again, go to the right side, smaller. Now we put it on the leaf node of this original leaf node, right? Just to put it on the leaf node, just traverse and go to its right location. Similarly, if it's 59, smaller, larger, and then just go here. Right? But insertion is easier, but deletion is actually very difficult because like if we delete, for example, this node, we have to reconstruct, similar to the heap, right? We have to reconstruct this site to make sure it still follows that specific data structure. So there are two type of situations. One is, let's see, we want to delete this node, and first, if it doesn't have a left child, so it will be easier. We just remove this node and put its subtree, like right subtree, to its parent node. This is like an easy situation. Like it doesn't have left child, but if it does, this is an example. For example, I think it's But if we want to remove 10, it doesn't have left child. We just remove it and point 16 to its parent. This way, it's still a binary search tree. But if it's this tree, it does have a left child. It might only also have right child. So, but this time it will be very complicated. We need to find its. We need to find its. So this is a. This is a node we want to delete. We just go right side all the way to this node. We call it rightmost. Basically, we just traverse right children, all the way to this node. It doesn't have right children anymore. This is like in this subtree, it is in the rightmost position. And now we just replace this one with the original one, and link this one to, I think it's, let me see. Yeah, that's right. So we put this, we delete this node and put this rightmost node to its current node. Like this is the one we want to remove. That we remove this, put it here, this one, and this one. As beginning is connected to this rightmost node, but this time we connect it to its children, its parent, because this one is moved here and this one connected to this. It's a little bit complicated. You can see, so after we remove that one, so this one now comes to here and this one connect to its parent. It's a little bit complicated because we have to maintain that data structure. You can see it's here. We want to remove 10. We just 20. Also, this question, this example, it wants to remove the root, so change the rightmost with the current one and point its children to its parent. So point its children to its parent. It's actually quite complicated. I have already shared this script to Moodle. You can see it's
You recommend me to code or no?
You mean code this one?
This one?
That's a good question. Ideally, you should, if you can code it, you will understand everything, but it's too complicated. I will suggest you try to code it first, and whether it runs okay or not, you can compare with the correct results and see which part that will be quicker. it's a little bit complicated to implement these typical things.
When you work in a job and you have a bachelor of computer science, they don't just look at the degree and the mark. They will take you to the coding screening.
That's right. They will ask questions that need to use binary search tree to answer that. So you can see you will be given a question, you will answer like, okay, I can use binary search tree to answer this question, and that's it. They will, but usually they won't let you give you 10 minutes, you give me the binary search tree class. They won't ask this kind of question.
So when IBM and Amazon and software development companies asking questions like binary search tree on interviews?
They might, but they won't. Usually they will ask you to do pseudocode, like we.
But in order for me to get into a job, so I can live on my own, I have to be able to understand it.
I know, yes. So for example, they will ask you, what is how to delete a node in binary search tree. Your answer will be one, if there's no, if there's a left children, if there's no left children, I just delete the node and put just using regular words to sentences to answer this question. That should be fine. You don't have to write a Java code to answer that question like this way. Actually, you can see the insert is very simple. Just find the leaf node and put that node. Create a new node and put to that children of that leaf node. And deletion will be a little bit difficult because you can see it's a very long piece of code. You need to consider two cases. If there's no left children, that's easier. Just remove that and point to that current node's parent. But if that node does have a left children, you have to make sure find the rightmost one and replace that one with the current one, and then assign its children to its previous children, like parents of rightmost. It's a little bit more complicated. You can give it a try by yourself, like implement it, and then compare your results. I think that's the best way to learn data structure. First do it by yourself and then compare it with the results. So
Microsoft PowerPoint is data structure.
Microsoft, sorry,
PowerPoint.
PowerPoint. Oh, you mean the software?
Software.
I don't know. I think so. I mean, almost every software you need to use certain kind of data structure. It's just complicated or not. You need to search, right? In PowerPoint, you need to search, and that should be maybe binary search or other type of search. Right. Yeah. So once we have a tree, we need to traverse this tree, like access every node in this tree. So there are three types of traverse: in order, post order, pre-order. Basically, just to determine like how you visit all these nodes. So this in order, this first visit the left subtree of the current node, and then the current node, and then the right subtree of the current node. You can see all these things as the code is written recursively. So recursion is a very intuitive way to do all the manipulations on trees. Because of this way, like left one, middle one, and right one. So it's like in an order, right? Increasing order. So in order traverse actually can give you an increased order of all the numbers in the tree. And so the poster order is similar, except just the left tree, right tree, and then after it, just the current node, which is the root. And also pre-order is the current node first, and then left to right. So they are, you don't need to remember these details, but especially in data structure 2, you will learn many algorithms. Some of them might use in order, some of them might use pre-order. You will be more familiar with it at that time. And also there are two very popular like terminology called the depth first traverse and breadth first traverse. If you learn some algorithm in, I think it's for example, the 8 queen and something, there are many famous algorithms. They use this DFS. So DFS just visit the root first, and then left children, right children. You can see it's a kind of that pre-order traverse is a kind of a specific type of DFS. BFS, it's visit root first, and then all the children. It's like from the left, like same level from the left side to the right side. This kind of traverse, usually you might need additional links. For example, for this tree, there's no link between these two one, right? So it would be a little bit difficult. For example, if I want to traverse these 3 nodes, they are in the same same level. I have to this one after I have to go back, and this one will be difficult. But BFF sometimes used in some specific trees, not just a binary tree. There might be a link between nodes in the same level. Will make the traverse more easier. You can just like a next neighbor, go all the nodes in the same level. So, unfortunately, Java doesn't have this tree class, so we cannot use it like a stack or queue. But a tree can be defined using the the collection class, and so. Yeah, I have already showed this class, and also we have a test BST. Basically, once you define the tree, we can insert a node or print out a node or traverse it. Just using in order or sorted order. It's all implemented in this BST, the Java file, class file. Feel free to read it after class. I think there are some external libraries Java support, and you can directly use tree. And also, we talk about that tree set and tree map. Those two are can also be used as binary search tree. All you need to do is just construct it in some specific way. So the last thing we will learn is called, this is a kind of application of binary search tree. It's called Huffman coding tree. This is an example. For example, in ASK2, usually every character is encoding in 8 bits. So if a text is 800 characters, would be 800 bits. It's need a lot of memory. But if we use Huffman coding to code it, we can just using the frequency to code out these strings, and so use less memory to save all these characters. This is an example. So the word Mississippi, we can actually encode it using this binary search tree. You can see it's binary, and the left side is 1, the edge is 1, the right side is y edge if we quantity that's sorry, the left side is 0, right side is 1. And a node either represent a kind of character. And for example, M here, you can see it's 0, 0, 0. We can reach M, and which means its frequency is 1. Similarly, T is 0, 0, 1. We know binary here, 0, 1 means 1, right? But I mean, in the frequency table, 1 represents 2. So we can just using this table and this specific tree structure to figure out how many characters are in that word. And so one last, based on this, let's have one last bonus question. What do you think if I encode a character, I mean a few characters using this structure and obtain this binary code? What does that binary code represent? You can check this table, see what that. This binary code can correspond to 3 characters. sorry. A? No, 3 character. It's so this code is just based on this tree and all this code. So it's 3 characters from these 4 characters. SIP? Okay, you got it. Yeah. So it's just 0, 1, S and IP. And yeah, that's it. So the way to construct a Huffman coding tree is just we first get the frequencies. So M just 1, S is 4, and I1, P2. And when we then choose the two character that has the last weight, like the last occurrence, and we merge them to a binary tree. And its mother, I mean, it's their parent is just the sum of their occurrence. And this after that, we choose the smallest one and merge it again. For example, 4 and merge it with this one. You can see again created this new tree. I mean, maintain this structure, and their parent is the sum of their occurrence. And we just again include this one, and this will be the final Huffman coding tree. And the left node, I mean, left edge is pointer is 0, right pointer is 1. Yeah, that's a way to encode the sequence strings. Yeah, that will be all for today. Just a simple introduction to this chapter. You will learn more about it in data structure 2. Yeah, this is our last lecture. There's a tutorial next Monday.
Can I go and do the tutorial tomorrow?
Yeah. Feel free to come. I'm in the second floor, 24 Queen Street. There's a sessional lecture room. I will be there. Yeah. Sorry. Oh, it's not mandatory. It's you can you have like you have a question, feel free to come. Yeah.
Because if I'm done university in next couple of years and I'm gonna get a coding job or software engineer job, they're gonna take me for data structures interview. I have to pass that.
Yeah. That's right.
So I have a question, what application, my question to you is that which applications do we use?